Hi, my name is William Borom, and I'm with my partner Aditya Shetty, and this is our project, Edge-Based Vision Assistant. So what we tried to do with this project is essentially implement an open source version that runs on a cloudlet of the popular Seeing Assistant apps that you might find from Google or Microsoft. How we did this, our system architecture, basically, we have an Android application that contains about 30% of the code. It used things like the text-to-speech engine and other things, sending things over this thing called the Gabriel System Server Architecture to a server that's running inside of a Docker container. This server does a couple things, such as YOLO for or object detection and relations between objects, calculating those, as well as providing some kind of caption to that image that it gets as a frame from the phone. For the image captioning, the user can toggle between an Azure service, which isn't really open source, but it runs better, and if you call it at a slow enough rate, it's essentially free to the user, as well as they can toggle between the completely open source version that we trained ourselves, called Show and Tell. So with that said, I'll hand it over to my partner, Aditya.
So, like Will mentioned, there's a couple of existing applications. The first is Microsoft Seeing AI, which runs based on Azure Scene Description, but it is a closed source service, and this could end up costing money to the end user. And then there's also Google Lookout, which is a service that is free, but it only provides object detection. It does not do any sort of scene description. So the fundamental idea of our Vision Assistant is to be able to combine both object detection and scene description in order to provide a meaningful representation to a visually impaired user. And we utilized a couple of features to take advantage of that. The first, we used a real-time version of the im2text show and tell static image scene description model. So this was a model that was originally developed for captioning of static JPEG images, like the kind you'd find in a newspaper with a caption underneath. We basically made a real-time version of that so that it could be utilized from an Android smartphone camera input. Some features that we added to make this more usable is we added perceptual hashing. This basically computes a hash on an image and will only perform a new calculation whenever there is a significant difference in the underlying hash, which means that the image has changed enough. This prevents unneeded computation and also alerts our user that whenever there is an update to the description, that there is actually a meaningful change in their environment. We have a remote start script to basically deploy our Docker container on our cloudlet to make it easy to sync between the different versions. And here's the main bread and butter of our implementation is we have a bounding box and object label model that is uses YOLO. So that runs in its own thread parallelly. And then we have the scene inference model that is using show and tell, and that runs in another thread concurrently at the same time. And so we trained the YOLO model is a pre-trained model that has about 80 distinct object classifications, and the show and tell model was one that we trained on about 80,000 images, each with about 5 captions, so about 400,000 captions. So the scene inference is provided there, and that total result is returned to the user's application, where it is passed to the Android text-to-speech engine. And then finally, just like a quality of life feature that we have is we wanted a visually impaired user to be able to toggle certain features, but the way most visually impaired users interact with their smartphone is through a screen reader, and we didn't want them to utilize the screen reader to see our buttons while they were also using the text-to-speech of our application. So we enabled accelerometer-based input changing, basically by shaking the phone in a certain direction, they're able to toggle certain inputs. And so here is a proof of concept of what this should end up looking at. Here is a depiction of an Android phone pointing to a kitchen. The scene description comes first. It basically says you're looking at a stainless steel refrigerator within a kitchen. And then the second part is the object detection. So it detects 3 objects, a refrigerator, a sink, and a laptop. And it provides them along 2 axes from top to bottom, and then also from left to right, the positioning of each of those objects.
You are looking at a living room with a chair, a computer, bookshelf. From left to right I see a dining table, a laptop, and a clock. From top to bottom, I see a laptop, a dining table, and a clock. If you would like me to stop listing the relations, move the phone up and down again. You are looking at a living room. From left to right I see a chair, a clock, and a TV. From top to bottom, I see a TV, a clock, and a chair. If you would like me to stop listing the relations, move the phone up and down again. You are looking at a chair inside a room with a coffee table and a large table with a. From left to right I see a chair, another chair, and a dining table. From top to bottom I see a chair, another chair, and a dining table. If you would like me to stop listing the relations, move the phone up and down again. You are looking at a room with a wooden floor. If you would like me to list the relations of all objects, move the phone up and down. You are looking at an office area with workstation with a laptop on top desk. If you would like me to list the relations of all objects, move the phone up and down. You are looking at a refrigerator with various appliances and a. From left to right I see a refrigerator, a sink, a bowl, a microwave, a bottle, and another bottle. From top to bottom, I see a refrigerator, a microwave, a bottle, a bowl, another bottle, and a sink.